So today we're diving into something called rmsynth. It's a new quantum circuit optimizer, and on the surface, it looks pretty cool. But the really fascinating part is that it's built on some surprisingly old math, which of course immediately makes you wonder, hasn't this all been done before? I mean, let's be real, it's a totally fair question, and it's exactly the one we're going to unpack today. Because once you start digging, the answer is way more interesting than just a simple yes or no. So, is the math new? Well, yes and no. I know, that sounds like a total cop-out, but stick with me here, because that contradiction is the key to what makes this project so special. To really get it, you have to split things in two, the math and the mission. Let's tackle the math first. All right, so let's start with the no part of our answer. The core mathematical ideas that are powering rmsynth, they are absolutely 100% not new. In fact, this is a pretty well-traveled road. This whole field of what's called Clifford+T optimization, it's been around for about 15 years. You can see the breadcrumbs going all the way back to 2013 with foundational work on phase polynomials. Then you've got key players like Selinger making big contributions. Heck, we already have established tools out there that do this kind of thing, like PyZX and Graysynth. So yeah, if rmsynth were trying to claim they invented some brand new math, that would be a huge red flag. But they're not. Okay, so that raises the obvious question. If the math is old, why on earth build a new tool? What was missing? Well, it turns out there was this really critical gap in the landscape. All the existing tools, for one reason or another, just weren't cut out for certain kinds of high-stakes jobs. The tools that came before pretty much fell into one of three buckets. First, you had the academic prototypes. Brilliant for a research paper, to prove a concept, but they were never built for speed or to be used at any real scale. Then you had the heuristic simplifiers. These are great on average, but they're kind of a gamble. They come with absolutely zero guarantees for how they'll perform in a worst-case scenario. And finally, you had the super specialized tools that were provably optimal, but only for teeny tiny circuits, like 4 to 6 qubits. Anything bigger and they'd fall over. You see the problem here? So the piece that was missing from the puzzle was a tool with a very, very specific set of skills. It needed to be built around a core idea of decoding. It needed to be obsessed with performance, and it needed to be engineered like a serious, reusable component, not just some one-off script. And that is the exact hole that rmsynth was designed to fill. And this brings us to the how. How is rmsynth actually put together? Because its design philosophy is just fundamentally different from everything that came before. We're not talking about a small improvement here. This is a genuine shift in architecture. So let's look at the old way. Most tools would take a quantum circuit, extract the core math from it, this thing called a phase polynomial, and then just throw the kitchen sink at it. A whole bunch of heuristic rules and tricks, basically just trying stuff and hoping for the best. The result? Totally unpredictable. There were no guarantees. Now compare that to the rmsynth way. It's night and day. It starts the same. Yeah, it extracts that polynomial. But then, and this is the key, instead of just simplifying, it decodes it. It finds the one true, mathematically minimal representation. From there, it reconstructs the circuit, deterministically, every single time. The whole hope part of the equation is just gone, replaced by a predictable, repeatable, rock-solid process. This really gets to the heart of it. It's two completely different philosophies. On one side, you have heuristics, which is all about, it's usually pretty good, but it's unpredictable and has terrible worst-case guarantees. On the other side, you have determinism. You get the exact same output every time, you have clear goals for what optimal means, and you can actually verify and compare the results. And for some applications, that isn't just a nice-to-have, it's an absolute non-negotiable requirement. You can also see how serious this project is just by looking under the hood at its engineering choices. It has a C++ core. Now that's a huge signal. You don't write something in C++ for a quick weekend project. You do it because you are serious about performance, throughput, and making it work at scale. It's also built to handle something called puncturing, which is a bit of a technical detail, but it basically shows that the creators are thinking about messy, real-world circuits, not just the squeaky clean examples you'd find in a textbook.
So all of these design choices, the focus on determinism, the obsession with performance, building for the real world, they weren't made in a vacuum. They were all made for one very specific, very demanding reason. And understanding this reason is what unlocks the entire purpose of rmsynth.
And here it is, the big reveal. The key to rmsynth isn't what it does, but why it was built in the first place.
This tool isn't just another optimizer floating around. It was engineered to be a core component for a system called Superdense consensus. And that, well, that changes everything.
See, a task that lives inside a consensus protocol has to follow an incredibly strict set of rules. It has to be deterministic, you have to be able to tune its difficulty, and it has to be cheap to verify. But most of all, it must be impossible to game the system. You simply cannot have unpredictable or exploitable results. So that old simplify and hope model, it's a complete non-starter. It would never survive. The deterministic architecture of rmsynth, on the other hand, is purpose-built for exactly this kind of hostile environment.
So let's bring this all home. When you cut through the noise, what's the real signal here? What actually makes rmsynth noteworthy, even at this early stage?
Let's go right back to that question we started with. Has this been done before? And now we have the full, nuanced answer. Yes, these ideas have been floating around in academic papers for years, and you can find bits and pieces in other tools. But no. No one has built something with this kind of serious engineering posture, this focus on performance and reliability. And nobody has done it with the specific intent of serving a mission as demanding as a consensus protocol.
The real innovation here isn't some brand new algorithm that's going to change the world. It's in the posture. It's in the careful selection of a problem that's actually built to survive in a tough adversarial economic environment. It's in the implementation, the decision to prioritize determinism and performance above everything else. And maybe most importantly, it's in the restraint. This isn't being sold as some final, overhyped solution. It's being introduced as a credible, reliable kernel. In a world that's just filled with bold claims and hype, this kind of focused, disciplined approach is what really stands out. As the source material puts it so well, that restraint is rare, and that, more than the algorithms, is the real signal. It's just a powerful reminder that sometimes the most important innovation isn't what you invent, but how, and more importantly, why you decide to build it.